Today we talk about a new concept. This is an innovation that nobody else has. And if every other blockchain is trying to convince you that their consensus algorithm is better, faster, more decentralized, I am now telling you that you can have a blockchain that uses any consensus. Even better, multiple consensus algorithms. And the first piece of the puzzle is being able to implement these consensus algorithms as WebAssembly smart contracts in our WasmX execution engine. These consensus contracts themselves are consensusless because their state is individual to every node. Eventually, they produce data that is in consensus, the block and transaction data. But until then, they have their own persistence database, and these contracts need to be able to talk with other nodes by HTTP gRPC WebSockets. And with WasmX, these contracts can be programmable in CosmWasm, EVM, or anything compiled to WasM. These contracts can be used to produce blockchain blocks and achieve consensus on transactions and data. A couple of examples of consensus used by Ethereum and Cosmos chains and others, like Ethereum's LMD Ghost Proof of Stake, Tendermint's BFT-based delegated proof of stake, and so on. But from these examples, we will first start with Raft. And in the last videos, I have shown you two very important concepts. One, smart contracts as state machines that can be built visually. And two, the fact that we can already have consensusless storage, and we called that transient storage when I made the video. In fact, WasmX is a multi-VM execution engine that can execute different types of smart contracts on different types of storage, including transient storage, in-memory storage, and so on. So today's demo brings both of these concepts, the state machine interpreter and the consensusless storage, together. And it is the first step on the road to implementing the Raft consensus protocol as a smart contract. Now, Raft uses a timed protocol for leader election. Each node can become a leader, and each node randomly selects a delay of 150 milliseconds to 300 milliseconds after each node automatically considers itself a candidate and proceeds then to ask for votes from the other nodes. Now, the first step is to demonstrate that we can have timed actions, and even more, that we can send, for example, gRPC requests to another node from a smart contract, more specifically from the state machine interpreter smart contract. And all of this is done on data that is outside of the on-chain consensus approved data. Our smart contracts are WasM, so to have timers and timed actions, we need to use the WASI standard. So I have compiled the state machine AssemblyScript contract with WASI and with access to our WasmX SDK. And I have created this state machine, a simple state machine where a node can either be a sender or a receiver. Both nodes start in the active state once the machine has been created and initialized. But if we trigger a send event, and let's look at this diagram in simulate mode. If we trigger a send event, then we are in the sender state, and we have triggered a delayed action after 5 seconds, after 5,000 milliseconds, which raises a send request event. And this will execute a send request action that sends a gRPC request to another node. Now in our initial context, we actually set the other node's IP, and I will show that in a minute. But once the request is made, then the node transitions again in the sender state, and again we have this timed action after 5 seconds and so on. We have a loop here. Now, we can end the simulation and go on the other route. Once we receive a gRPC request, our state machine is transitioned to received, and immediately after 1 second, the state is transitioned again to active. And this state machine has as initial context the IP address of the receiver node and some data. And this is the state machine. I have already saved this state machine into our state machine interpreters for both nodes. So the state machine interpreter contract was actually saved on-chain, but the instantiation of the contract has different data per node. So locally, I am running a Mythos chain with 2 nodes as validators. And I have repurposed a gRPC ping method to trigger the node, the sender node, in order to become a sender. So let's start the process. We are sending this ping gRPC request to the node on the left. And it already started doing some things, and we will look in detail immediately. But we are seeing the first thing is that the chain does not stop. The chain continues even though the nodes are doing different things. So let's look at the logs that I made in the state machine interpreter. And we are starting with what happens in the sender. First, we log hello world each time the state machine interpreter contract is executed, and we can see this thing right here. Okay, and then we have sent the send event to trigger this node to become a sender. So we are here. And it has found that the next state in the transition, after the transition is executed, is sender. But sender has some delayed actions that need to be executed. So it is executing the delayed actions, and it actually is waiting for 5 seconds until it executes. After waiting, it discovers that the action to be executed is raising a send request event, which it does, and it also finds the next state for the machine, which is the sender state. And if we look here, after the send request event, the state becomes sender again. And it is executing the send request, which is sending a gRPC request to the other node that is on this port. And that's what we are seeing on the second node. We have the hello world from starting the execution of the state machine. We've received a gRPC request. That gRPC request is then translated into a receive request event on the state machine, and this transitions to the next state, which is received. So we have the receive request event here. We are transitioning to the received state, and then we will see executing delayed actions. So after 1 second, the state is then transitioned to the active state, which happens here. So again, the node is ready to receive any other state transitions or become a sender itself. And this continues and continues and continues because the sender is in a loop, and this continues until the nodes are stopped, because that's how I created the state machine. Now, this is a first small step in the process of having Raft as a consensus protocol for a blockchain, but as a state machine contract. And having Raft as a consensus protocol through a state machine contract will be the first step to having proof of stake mechanism like Tendermint's BFT proof of stake as a state machine smart contract. And after that, you can have a blockchain that changes its consensus nature while running. For example, from Cosmos to Avalanche and back, you can have a chain that transforms itself into a distributed Raft database and back, a shared text editor that becomes a blockchain and back, and you can change the execution engine while running, for example, from EVM to CosmWasm. A blockchain can mix any type of consensus with any type of execution engines, but even more interesting, you can give birth to new chains of different natures than the parent chain by having a contract on the parent chain, and then you can even join the changes like a roll-up chain. And we propose a visual editor for these new types of contracts and to treat them as finite state machines. If you want to help the Mythos project, become a volunteer validator, and test the system, you can join our Discord.